Okay, we wanted to find the change in the velocity. Curvature was the change in the speed. So now we want to focus on change in direction. So curvature tells us how fast a curve turns. The principal unit normal vector will tell us the direction the curve turns. Now remember when we found the curvature, curvature was the magnitude of the change in the tangent vector relative to the arc length. So now to determine the change in direction, we'll just focus on dt ds and see how it changes directions. So to do that, we don't care about the length of the vectors. We just want to focus on direction. So we'll start by taking a unit normal vector, which will be a unit vector in the same direction as this dt ds. So if we just take dt ds and divide by its magnitude, we get our what's called the principal unit normal vector. That can be found by taking 1 over the curvature, which we have 2 formulas to calculate, times dt ds, because remember dt ds was just the curvature. So now that's not going to be the easiest form to use because finding the curvature itself was, pretty large task. So the formula that we're going to use though will be the principal unit normal vector equal to dt dt over the magnitude of dt dt. Now the main reason that this is a much better formula is that we don't have to worry about whether the parameter t is the arc length or not. But if we use this form of it, we had to have the curve parameterized using the arc length. So for any parameterization, we can find the principal unit normal vector by this form. So now, what do the properties of this principal unit normal vector have? First, t and n, remember t was your unit tangent vector, n will be your principal unit normal vector. Normal, the word normal means perpendicular or orthogonal. T and n will be orthogonal at all points on the curve. So if you are looking at the tangent vector here, the normal vector is going to be orthogonal to it. Or here's another example of a tangent vector. The normal vector is orthogonal to it. So t and n are always orthogonal at every point. That means if you took their dot product, it'll be 0, since that's true for any orthogonal vectors. The other characteristic that the principal unit normal vector has is that it always points to the inside of the curve. It's pointing in the direction the curve is turning. So n, to be orthogonal to t, could have gone this other direction, but that's not to the inside of the curve or the direction the curve is turning. So we don't care about that one. The n, though, that we're concerned about will always be pointing to the inside of the curve in the direction that the curve is turning. So let's find the principal unit normal vector for this helix. Well, the formula that we're going to use, the variable t, the parameter t in this parameterization, is probably not the arc length. And I don't want to have to worry about that. So I'll use the formula dt d little t over the magnitude of dt dt. So let's find dt dt, which will be the derivative of the tangent vector with respect to time. So first let's find the tangent vector, which is just simply r prime of t over its magnitude. It's the unit vector of the velocity. Well, first we need to find the r prime of t. Which will be a squared plus b squared, square root of that. Just go through your formula for finding the magnitude of that vector. So now, this will come out to be, let's back up, that's the magnitude of r I jumped ahead there. Here's r prime of t, the magnitude of r prime of t. Okay, so the unit tangent vector over the square root of a squared plus b squared. And it's each component divided by the square root of a squared plus b squared. So if I were writing that, now we want in this formula, we want the derivative of that tangent vector with respect to t. So let me rewrite this so that I have the three separate components. The minus a over the square root of a squared plus b squared is just a constant. And that last component is just a constant, since there's no t's. So now the derivative of t with respect to t, which is t prime of t, will be minus a over the square root of a squared plus b squared times cosine of t, negative a sine of t over the square root of a squared plus b squared, and then 0. So now we just want to make that a unit vector. So we have this vector Okay, find the magnitude. The first two, when you square them, we'll have sine squared plus cosine squared, and we'll have a squared over a squared plus b squared. And that's it, because the last component is 0. So that will simply be a over the square root of a squared plus b squared. And now take each component and divide by that, and you simply get minus cosine t minus sine t, 0. Now, notice that third component is 0. What that means is that this vector is actually in a horizontal plane. It's always going to be horizontal, so that that z component is 0. This minus cosine minus sine, if you remember a circle with radius 1 had a parameterization of just sine of cosine of t, sine of t. So this is simply the vector that's pointing inward from the outside of the circle. So if you take any given circle, the unit normal vector is constantly pointing to the inside of the circle, and it's pointing straight to the z-axis. It's horizontal. So um, the principal unit normal vector for this helix will always be pointing toward the z-axis, which is the direction of the curvature. Now let's check also, is T orthogonal to N? Let's see, where is T? T was the vector that we had over here. So if you took minus cosine times the first component, you would have positive A sine T cosine T over the squared, and then you'll have minus A sine T cosine T. So you do have that those two are orthogonal. So that's a good way to check yourself, is to see, is T and the N that you come up with, are they orthogonal? And then T here points in the direction the curve is heading, which is true by this. The direction of this would be the minus sine T cosine T, which is that tangent vector. We saw that before. Just take the derivative of this, and that goes along the curve. And then N points to the inside of the curve.